1 o'clock Eastern. We're kicking it off. Good morning, good afternoon, good evening to everyone who's joined. And we're going to wait for, we're going to get started while more people trickle in. And so welcome to today's TileDB Tech Talk. I am very happy to bring you our April edition. We've been doing these monthly for the past 6 months now. My name is Devika Garg. I'm the Director of Product Marketing here at TileDB, and I'm joining you from NorCal. And today we will be hearing about population genomics applied for diagnostics in the rare diseases space for newborns. And from two of our experts at TileDB, very own Jeremy Leipzig, Product Manager for Population Genomics Solutions, and Chase Christensen, Staff Solutions Engineer. We are in such good hands. So great to have you both here.
Great to be here.
Absolutely. It's exciting.
I have a couple of housekeeping notes before we get started. So please add questions in the Q&A panel anytime during our presentation. We will tackle those at the end. Also, we do have a raffle as always at the end. So stick around. So raffle for $100. Really nice, sweet. And so before we go in, let's see. Let me see if our slides work. We don't run into Zoom issues. That's our talk for today. And let's go into an opening poll, short poll, to understand where you are with large-scale genomics data today. If you could take the time to answer, would be helpful. And I think these are nice questions. Like, Jeremy, like, what do you think? And Chase, what has been your biggest challenge of downstream analysis?
Well, speaking for myself, obviously, I'm a little bit on the engineering side. So presentation, which can mean anything from building notebooks to dashboards to static reports, tends to eat up a lot of my time just because there's this cycle of going between my own work and the end users and different stakeholders who want different facets of a result. So I'd say that last step eats up an enormous amount of time for analysts and myself included.
Yeah, absolutely. And now from my perspective, I deal with a lot of the systems side of things. And when I work with customers, when I talk to folks, I think the big issue with all three of these that I see and I support is managing a lot of the infrastructure to take this, managing those API calls, managing all the enterprisalities that come into doing this, right? You want to make sure that when you're unlocking a lot of that value within your organization, you're keeping yourself safe. You don't want identified information leaking. But then when it comes to analysis, how do you scale your infrastructure? How do you handle all of that increased demand and store things and do efficiently so that not only are you spending time on data engineering, but you're spending time on doing it effectively so that you're not blowing up your budgets. So that's at least what I see out there.
That's interesting. So we're seeing like the polls come in, and actually maybe we have 8 of you answer. Let's push it a little bit more. What do we see here? So we see aggregate queries as one big challenge, and integration with clinical and PopGen data. That seems to be the biggest. Second question, I think we'll get varying answers, right? Always people spending a lot of time on data engineering, nearly not enough time doing the actual, in the insights layer.
Right.
Yeah, it's very interesting.
Yeah, 63% there.
Well, I think that's very typical. So, I mean, in my experience, people have to work at a layer lower than their job title or where they're really comfortable. So, a scientist has to spend a lot of time doing data engineering. A data engineer has spent an inordinate amount of time doing DevOps and so on. So, really, the idea of enterprise software like TileDB is that it does a lot of that work for you. So you can spend more of your time doing your actual designated role of what you're trained to do, and less time munging around with infrastructure items, with making queries that are parallelized over large data sets. That's really built into TileDB.
Yeah, and as you start to scale, like once this goes from kind of a prototype, right, something that you've got a proof of concept going, and you start to really scale this and put in production, we know that to scale, you have to specialize. And that's what you see, right? Is it the most valuable time to take someone who's got 1% and force them to go lower down the stack when there's still additional value to be added, especially if, as you start to get lower and lower down the stack, are you getting farther and farther away from your core product, your end customer, or your end result? And then instead of focusing on what's driving a real outcome for you, you're focusing on just the day-to-day operations, and that can definitely impact projects.
Absolutely. It was great. Let's thank you everybody to take the time to answer these. These are definitely helpful. Let's keep going. Right. So our agenda for today is all about, so it'll be split between Chase and Jeremy here, talking about population genomics, the use case itself, or the technical challenges there, unpack and understand the architecture that TileDB brings and the advantages and impact. And then we'll last but not the biggest piece of this, the federated queries. So Jeremy, I'll transfer control of the slides over to you.
Okay, great. Okay. All right. Okay. Well, there's one takeaway I want you to have from this talk is that rare disease is a bit of a misnomer. So while each rare disease individually is rare, rare disease as a whole is not that uncommon. And these are manifest in children. And we have statistics that back up that claim. And many rare disease of a genetic origins are monogenic. So one gene is involved. The variants themselves are often causative. So they have a highly penetrant variants that if you actually manifest these variants, they almost always cause the symptoms of the disease. And then finally, there's many inherited diseases where we have actionable interventions that we can take. So of that list, these are ripe for newborn screening in particular. So why do we have to screen newborns as opposed to babies at their first well visit? Well, for a lot of diseases, there's a great chance to have a rapid diagnosis can really affect the progression or the outcome of the disease. So there's diseases like the skid diseases, like bubble boy diseases, congenital adrenal hyperplasia, galactosemia. Well, these are diseases where it's best to actually have an intervention as early as possible. And many of these interventions are not exotic gene therapies. They can be as simple as a change in diet. Okay. Can we get to the next slide there? Okay. So there's actually many ongoing studies and pilots to investigate the feasibility of newborn screening throughout the world. The one we're going to talk about today is BeginNGS in the lower left. All of them are quite worthy. I'll say BeginNGS is special because of the transparency we bring to the openness and publications that we have out there. We have a transparent explanation of the variant curation and refinement process. Our queries are in GitHub, and we have a willingness to take on new hospital partners throughout the world, foreign and domestic. So I want to distinguish what's going on at Rady's from what's going on at BeginNGS. So Rady's is really about bringing out diagnosis of diseases for sick children. BeginNGS is about screening healthy children. So on the left, you see Dr. Kingsmore. He has his Guinness World Book records for the quickest turnaround for a diagnosis of a newborn. This is his day-to-day operation. TileDB helps with both of these initiatives. So on the left, we have a way where we can bring diagnosis of children using low code dashboards. We have many ways of allowing queries to be performed for kids, and we have ways of allowing these BeginNGS queries, which are global and involve expanding. Sorry, we provide the foundation for doing BeginNGS queries, allowing many disparate parties to share ever-growing lists of variants, which are indicative of disease and growing these lists and block lists that indicate there are variants that do not affect adults. So we're getting information from both biobanks and kids in hospitals to better refine lists of variants of interest. Okay, so the ecosystem involves many corporate and hospital partners. As I said, we have TileDB for the database. We have Fabric, which provides the pathogenicity predictions and the ability to actually infer how variants are related to disease. We have Genomic, which provides literature analysis. We have AWS for the cloud platform, and we have Illumina as our sequencing partner. So for pharma, our platinum partner is Lexion. They've been very helpful in getting us access to both biobank data and the ability to analyze variants as we assess them from literature and our algorithms. So the main hospital leader is Rady's, but we're expanding that throughout the world. I should say the biobanks have been extremely important for refining the list of block listed variants that we know do not cause inherited diseases in children. So there's the BeginNGS logo. All right, there's two important publications which go over for BeginNGS. The first is kind of a pilot project that happened in California for various NICUs that really proved the feasibility and the practicality and the expense of doing newborn screening for children. On the right, we see more of a deeper dive into using these block lists and training on healthy lists of variants from adults. They're both valuable papers. I'll say, as you see, the number of variants of interest has exploded incrementally as we get more and more variants for children from our growing list of hospitals and also a growing list of biobank resources from large population studies throughout the world, but also from what we get from dbGaP and other public resources. So, I mean, one of the reasons TileDB is so suitable for producing both these kind of ad hoc queries that are used in the diagnosis of children on a daily basis, as well as powering these like longer queries that are useful for BeginNGS and other consortium projects, is that we are a database that's both performant and scalable. So we're performant, then we can have a very quick turnaround for queries, regardless of whether they happen in a web platform, in a command line atmosphere, or using APIs that are either remote or that live within our ecosystem. But also we power these long-running analyses, like for BeginNGS, where we're hitting a small snippet of code that's dispatched over large sections of variants from thousands and thousands of people. So you see, what we can take is many different inputs and then support long-running analyses that are downstream. So they could be GWAS, FWAS, EQTL. We can do phenotypic screens, pharmacogenetics. But we also have these kind of interactive tools that we support in our dashboard. And when you get something in the dashboard, we can actually support the security, the authorization of users. So you're doing this in a very secure atmosphere. So here we see our variant browser. This is what I talk about, like an ad hoc query. So you might have gene of interest, you might have subjects of interest, you might have VEP annotations that you want to filter down, you want to have like nomad allele frequency calculations that you want to use as a filter. And then you might actually be involved in other downstream annotations for samples. So you might have certain phenotypes that you want to filter for. Most of our queries are like 30-second turnarounds, even if there are thousands and thousands of subjects that you're performing these, even if you're tying in many, many different tables. So these turnarounds are very typical, for biobank sources, for children's sources. And this is a very low code solution we have that's extensible for a number of backends. So for Rady in particular, they use Fabric for their pathogenicity predictions. And then we actually allow them to drill down to about these reports that are essentially driven from the phenotypes from the kids themselves. So you have a lot of data that's going into these predictions. I have to hide the identifiers obviously here, but every pathogenicity prediction for an individual kid comes from one of these phenotype reports. It shows the most likely variant causing that disease. So, I mean, I think Chase will chime in a little bit here about kind of the overall themes we're talking about.
Yeah, absolutely. Absolutely. Do I have control? Do I have control? Let me see. Click start. Make sure I can move ahead. Awesome. Awesome. So now that we talked about that use case and we talked about a lot of what you can do with this data, we're going to talk about why we're seeing good demand for this type of data. And we're also going to talk about how TileDB uniquely supports these type of data engineering and these data initiatives. I think we can all agree that data is important. And I think we can all agree that the world is multimodal, right? When we start to structure and bring data into our systems, we don't just have tabular data. We need images, right? Maybe we have graphics, maybe we have, biomedical images, etc. We have all sorts of VCF data, single cell data. All of this data has different file formats and different ways to access it. And we know that it's important because if you want to build a full story beyond just a single image or a single file, you need access to a lot of the data, and you need to be able to bring that data together to test your hypothesis and work towards initiatives you're going for. And we know this is incredibly valuable, but as we're going to touch on, it's incredibly complex. Again, juggling all these different formats, these different systems, these different APIs, it can lead to a lot of toil, which is kind of tactical, linear and scaling work that's not super great, instead of letting you focus on innovation, which is really what drives you and your org and everything you're trying to do. Let me see if I can go next on the slide here. Zoom in, next. Awesome. And I think what we're seeing is that organizations are putting an unfair expectation on their teams. I think Jeremy hit on this previously when we talked about going lower into the stack or going into a part of the stack that you're not necessarily trained on, you're not necessarily the right tool for the job. We're starting to really ask teams to be stretched more and more instead of focusing on the core problem that they were brought into the organization for. And this is causing businesses to look at maybe a research or a scientific persona and say, hey, can you be, you're a data engineering team now, right? Like, hey, you can just be our data engineer. And then maybe say, wondering where did more of the scientific work? Well, why didn't that get to the sunlight there? And the answer is because they're focused on data engineering. And there's a lot of complexity in data engineering. There's a lot of complexity in systems, especially anyone who's spent any time really working on pure infrastructure. It's sometimes a miracle that any of this works, and that's why people tend to go cloud native, et cetera. And if we go to the next slide here, and this is because of this growing technical challenge, right? As we start to bring in more and more data, data engineering is no longer as simple as we thought it would get to, right? We've figured out maybe how to manage one modality, but when you start to explore different modalities, you start to explore different tool sets, et cetera, you run into a lot of problems. One example of that problem is the N+1 problem, which is how do you process data? You maybe have a batch ingestion of a bunch of data, and then you want to add an additional data to that, an additional entry. Well, if you want to do population level analysis, right, you want to understand values that represent the entire data set. Well, do you have to reprocess that? How are you tracking that? How do you store those files? Are these individual files? Is this one giant file? How do you do this efficiently? And we're going to touch on what that means to do this efficiently beyond just having a bunch of files. And then how do you do all the things that are important for FAIR, right? How can you make sure these are findable? How can you make sure that you can access them? How do you make sure you can use them in different ways? And how can you make sure that you can share them and do everything you need to do? And this is all part of this data engineering that we've pushed on to different personas who necessarily haven't specialized in this. This is an example showing what happens, right, if you have a bunch of single files and thinking about how do you store these files close together, right? How do you make sure that you're not accessing data that you don't need to access? How do you make sure that you're processing data in an efficient way? And then if you go to the next slide, then maybe you combine it into one giant file, but then what happens when then you add new entry? You have to update that file, deserialize it, et cetera. Again, kind of in the weeds here, but these are things that we need to think about when we're managing data engineering systems, especially as we begin to scale. So where does TileDB come in? Well, TileDB comes in because we're actually changing the way we want to think about this. So TileDB at its core is an array database, right? It is a way to take these different formats, bring it into a more programmatic friendly format, the array. And so when you think of how to bring things in and out of memory, deserialize things, data locality, all these access times you need to think about, right? Your performance through access. TileDB, first off, uses the array to do so. Whether it's a dense array where you've got everything populated, or a sparse array where you can represent the data in a way where not every value has an entry, but you can compress that and you can make it serialized on disk so things are still efficient. What we did is we said, listen, let's take that VCF model and let's build it with arrays and make it more effective and more programmatically easy to access so that you can solve all the N+1 problems we discussed before. So it's actually a new data model, but you can ingest those original files into this model and access it in the ways you want. And I think there's a delay here. Going next. And beyond that, and this is like a deep dive slide, these are all the things that we have to think about, right? As you think about how do you order your data once you store it on object, right? We're backed by object. How do you order that data within object so that you keep what needs to be close together. So you can efficiently only bring what you want in memory. You don't have to parse large data sets in a way that's inefficient. As well as you don't have to store empty values, right? This is very efficiently stored on and off disk. And I think that's what's really critical here. But these are the considerations that a data scientist, or not a data scientist, but a data engineer would have to be considering. And TileDB has worked to offload into these new data models with our APIs. And of course, hitting on this, these are all the other things you must consider, right? A file format in an array is not enough. How do you efficiently store it? Do you want to compress your data if it's not being accessed frequently, or if you just want to save on your costs? What happens when many users want to access this data, have reading and writing to it, etc.? You want to maybe do time traveling, and then how do you make it very performant, optimize it? When you're bringing it into your systems, how can you make sure that those systems are efficiently processing that data as you begin to scale, especially for large jobs, right? And then can we use this to give you faster feedback loops? And that's really like the full story of TileDB's superpower. So the superpower begins with that array structure that lets you build new data models or use data models that we've done to help offload that data engineering, whether that's single cell population genomics, biomedical images, right? These are all different variations of arrays and grouped arrays that we can build to help you efficiently do what you do best. And we abstract that away with APIs, right? We want to integrate with the tools. We want to use the APIs and the languages that you're familiar with, whether that be Python or R. We have libraries that can support those. And then once you start to gain all this value from 1 and 2, right, you have these vertical integrations with your tools, you have these fast data structures, and you're getting really efficient. We have all the non-negotiables when it comes to an enterprise, right? And that's the access control, who can access what, when, and where, logging on who accessed certain data sets and ran certain operations on that data sets. And we have all the HIPAA and all the important SOC 2 compliance, GDPR, that you need to ensure that you're making the right thing easy to do. And that's really the whole goal of TileDB as a platform.
That's great. So outcomes. Yeah, so I want to talk a little bit about the outcomes of what we've done for beginnings. As I said, we're trying to expand globally, and although I'm not privy to actually expose where we're going to expand. It includes both hospitals in Europe and the Middle East, as well as the States. You can see some turnaround time. We've had tremendous success helping Rady individually diagnosed kids. I'll give you a bit of a statistics for VCF. We have a 97% cost reduction. I'll admit that's a little bit of a straw man. Not everyone uses raw VCF files to manage their genomic data, but we also compare very well to standard e-commerce databases or general databases designed for data science. Okay, next slide. Okay, so as I said, we're expanding globally. What that actually incurs is a need for data sovereignty. What we want to do is basically share genotype and diplotype counts because we cannot share someone's entire sequence, okay? We can't even share their identifiers or identifiable information. And we don't want to share static CSVs, okay? Because these are, what we really want is live queries of variants of interest in the block list that's growing on a weekly basis. Okay, so there's some programmatic decisions surrounding edge cases that we need to develop and query over every participant, every stakeholder in the system. I'd like to get to the next slide if we could. Okay. As I mentioned, sovereignty causes problems. The data privacy issue is very important, and that's why we have the federated query. So I'll talk a little bit about the specifics of that query. But first, I want to get into the flow of the stakeholders. Okay, so for the stakeholders themselves, they're accessing genomic data, phenotypic data. There could be some experimental data, some batch effects that need to be accounted for. And then they want a variety of queries to come out the other end. So that includes aggregations, which is complex counts of certain variants and diplotypes that occur within genes for individual patients, but aggregated over the entire data set. Often they want high-level summary statistics. They might want something like a beacon, like a GA4H GH beacon. So you say, well, do I have this variant or don't I? Or they want views of tables. And the stakeholders, as I mentioned, are research hospitals actually doing the research, biopharmas who may have certain drugs in the pipeline that are relevant to the diseases that are being detected in these newborns, and then diagnostic providers who really want to institutionalize or upscale these tests globally. And TileDB sits in the middle of these organizations. Currently, the specifics are the federated query runs on thousands of patients in under 10 minutes. Okay, we have our variants of interest that are mined from ClinVar, but we also have this block list, and the block list basically tells us, oh, these are variants that they may be deleterious, they may be likely pathogenic or pathogenic, and they might actually shorten your lifespan in adult onset. But for newborns, they're not particularly relevant. They're not associated with inherited diseases, severe inherited diseases in newborns that would be useful for a screen. Okay, 342 genes. These all been handpicked and curated based on what I spoke to before, which is they're actionable. So there's an existing intervention we can apply to these diseases that are associated with these genes. So there's some reason to do the screen, and then funnel those kids to providers and get the care they need quickly. Okay, so if we look at what gets baked into the UDF is really just a snippet of code that you use to dispatch over large data sets. So that code could be Python, could be R, could be any number of languages, but the point is that it's a very customized piece of code that the data owner writes for the benefit of the consumers, okay? What we do for the federated query is that we inject a key that gets securely baked into that UDF and then allows you to share that with other users and perform dynamic queries on your data on their behalf. So they're running the queries and they're actually able to dynamically query your data within certain parameters. But the end result of that data has a certain schema that you have chosen. So you can't, once you hand over a UDF, you can't go willy-nilly and access data sets that it wasn't meant for, or access views that are that you had no intention of handing over. Okay, so as I mentioned, that second paper really got into start to leverage what we learned from the biobanks to get that block list. And that block list is not that long, but it generates just so many usual suspects. You saw that if you weren't using the block list in those healthy biobanks, you would have had a huge number of false positives, so 73%. And then using that block list, found a number of variants that reoccur in adults but actually don't cause severe disease. And so that's been really important to grow that. And that can't be grown until we have enough healthy adults at our disposal in order to see, oh, these occur in underrepresented populations, or in certain situations we just didn't see that these would occur in genes that we want to grow or add to the list. So growing that block list is a major component of what we want to support with the federated query. Okay, so the currency of what we're doing in beginnings is these diplotypes. So the diplotypes are essentially variants that co-occur or reside in the same gene in certain individuals. So we don't reveal the individuals, but we do say, oh, this combination of variants occur in 3 individuals, for example, and these are putative compound heterozygotes. So we have at least some evidence that they came from mom and dad, but we don't know because we don't necessarily have phased sequencing for these cases. In the majority of cases, a few of them do have some phasing, either based on reference, haplotyping, or trios, or what have you. But for the majority, we just have to kind of assume that one variant came from mom, the other from dad. But for other modes of inheritance, it's a little more clear cut. But all the curation happens on diplotypes. And the reason I'm talking so much about this is because if we just wanted to provide like a convenience table, like variant counts or allele counts that's pre-computed, that wouldn't even have it happen dynamically. Like this has to be a programmatic exercise that we do to hand over diplotypes. So it's not a matter of, this is not something we can pre-compute and then suddenly hand them over as a static report. This really has to be a dynamic process that's supported by the federated query. Okay, so the mechanics of the build and share of the UDF is actually pretty pedestrian. We have a panel generated form here. You fill out the specifics. I will mention that, so we have support for different AWS regions for where the actual UDF runs. For example, we're required to run UK Biobank queries in EU West, but for data sets that are in the US, you probably would just want to run where they natively reside in your buckets in the East. And this is where you inject that key. And that key really gives you the power to allow people to query your data securely, but within the confines of what you laid out. And so this is where the sharing would actually happen. This is what using the UDF looks like in a Jupyter notebook. You can see what we package with the UDF is a Python package that knows how to speak to the UDF. So you can use that as it provides APIs and commands that really let you like reveal what the UDF knows about your data. So for this, we've cooked up a function called beginnings, and that reveals the genotypes and diplotypes from that pre-cooked federated query. Okay, so this is Dr. Kingsmore kind of giving a very high level congratulations to us for helping him with our the turnaround time he's had in the NICU. And he's someone who really realizes that this has to be like a matter of doing like many concurrent queries on growing data sets, which is why the federated query is important. Also why something like TileDB, which is really a database that's designed for discovery, is important for propelling these types of discoveries going forward.
Wonderful. Thank you so much. Like, I want to definitely thank our Dr. Kingsmore, Rady, for being such a wonderful partner for this work, right? And to Jeremy, you, Chase, for doing this presentation today. We do have a few resources here, links to which we'll also drop in the chat. If you'd like to learn more, we have a solution brief on our resources page. If you're interested in becoming a beginnings partner, or hospital or pharma, we have more information there, and you can talk to us to learn more. Jeremy, do you want to say something about our upcoming TileDB Carrara product, like the next version of what we have today?
So yeah, Carrara basically kind of provides a lot of improvements to the user experience in terms of both sharing files. We're going to have workflows. We're going to have a much more sophisticated views between namespaces and organizations. So this is all about rounding out the user experience from what has been kind of a high performance scientific database to something where you have a system of record for all your data. Okay. And this would kind of lay out that Carrara would be a part of everything downstream of primary analysis. So stuff that would typically happen in workflows, that's just transformations of data, going all the way to tertiary analysis and all the way to static reports. So that's one thing we've really wanted to have is like, do we attract end users or stakeholders who are not necessarily technical to log onto the website and see the results that are generated by these type of algorithms? And we want TileDB to be a place where they're comfortable going and finding the results they need.
Geez, any other thoughts?
No, I think that hits the nail on the head. I mean, talking about having this user experience. I mean, with TileDB and early on, I mean, Stavros has like a really, really great pitch on this when he talks about his vision for TileDB. But it was to build that technology first, right? Build that integration, that highly performant data management tool with arrays. And then from there, it's how you can get closer and closer to the user experience. How can you start with technology and then build a user experience around it to really get you end to end and really build and support applications that get you and your organization of value. And I think that's really what we see at TileDB and why Carrara is really, really exciting, branching into that secondary analysis with things like Nextflow, giving more of those the things we've seen out in the market asked for, and getting closer to that research and the scientific personas that can actually leverage a lot of the core engine and potential that we've been building over the years.
Yeah, nice. We have all three of those QR codes here, and we'll do a few Q&As. So I see one question from Andrew Warren. How fast are the queries for a single sample? Jeremy, if you
Right. So the main bottleneck for queries is really the size of the result set, not necessarily the size of the data. So everything is having it in parallel anyway, and sample is actually one of the dimensions of a TileDB VCF data set. So pulling a single sample in a single region, should be very, very quick, and we're talking a matter of seconds. So this is not go get a coffee, come back type of queries. These are highly interactive ad hoc queries that we support in our variant browser on the CLI. But even these don't scale. These scale in closer to big O log n rather than a linear speed, because the result set can grow quite large when you're looking at, say, dozens of genes over thousands of patients. But that's being essentially sent over the internet to your browser, where it's just kind of clogging the pipes, if you will. But that result set itself is the bottleneck of the query. So a single sample query can happen in seconds.
Yeah, and I think what's critical, right? Obviously, you need to touch data, and whatever you touch, you need to respond. But part of what you can do with TileDB is we actually will scale up the infrastructure for those queries, so you can be faster, so you can run more in parallel, and then aggregate it together depending on what you're running. So again, a single query is really fast, but as you start to talk about multiple samples or even different modalities of data, we can be really performant there.
Absolutely. We do have another question. Why do we need a database for variants?
Right. So that's a great question. Typically, we see a very common order of events is that we encounter someone who's done a lot of work to drum up a bespoke solution. Okay, something that's scripted that basically leverages a bunch of secondary analysis pipelines to look at their data. So something that's heavy in BCF tools or other command line tools. And that is great. That is fine for a single analysis. It's enough to power a dissertation. It's really enough for a Nature paper, but it's not going to work for an enterprise solution where you have many stakeholders trying to access the same data set with questions that you didn't even anticipate. So what we do at TileDB is we have solutions that can expand in terms of velocity and variety for a lot of different stakeholders, and that's really when people come to us is when they hit kind of a wall in terms of, okay, I built something that can do this one thing, but I can't service all these people.
Makes sense. Another one. Can you highlight how TileDB might help in multi-omics analyses? Example, VCF, RNA-seq, proteomics.
Chase, you want to take that?
Yeah, I think this is a deeper conversation, and this is something we can talk about. But once you do a one-time ETL into the TileDB format, so once it's in the TileDB format, and once you're in the TileDB data model, you can start to query and aggregate these different data in the format that you need to based on the results, based on the outcomes you're looking for. So thinking of instead of having these different file types and these different tools, you actually bring them all into our system. And again, we have single cell, we have VCF, we have these APIs, and then you can bring that data and aggregate it together based on your query results programmatically to start to give you what you're looking for from all these different data types. So we really skip the middleman of having to deal with all that ETL and then give you a way within a single system to bring it all together.
We do have some multi-omic notebooks. So the EQTL analysis uses SOMA and VCF.
Yeah.
We have, that there's three main verticals to our life science offerings. We have single cell, population genomics, and biomedical imaging. Now, TileDB is used by 10 of the top 20 biopharmas, and virtually all of them have a need for at least two of those verticals. I will say that there's very few that just come for one thing and then don't have a need for something else.
Yeah.
But we would be happy to talk to you about proteomics in particular if you have something downstream of that.
And we've also seen a demand for spatial transcriptomics, right? How can you have that spatial aware story using images as well as that single cell data? So
Awesome. Andrew has two, Andrew, thank you. So a compliment and a question. Blown away by the potential of this. If an independent developer such as myself wanted to build applications on top of this platform, what would be the biggest roadblocks? What would be the best way to get started?
yeah, I can handle this one. So for roadblocks, I mean, this is an it depends. I'm going to hit you with the classic solutions engineering. It depends, right? We'd have to really discuss what you're trying to do. But as for get started, we have a REST API server, right? We have a TileDB client. You can access things programmatically based on what languages you're using. You can make calls into the system, and so you can actually run that processing really close to your data. We're backed by Object. And if you're looking to just get started today, we have cloud.tiledb.com. You can sign up and play around with notebooks, as well just have a discussion. I'm happy to have a discussion on what you're looking to do and where we can go from there. But I think that's the best way to get started. We also have within cloud.tiledb, we have an academy, and you can search through academy, and there's a ton of different example use cases and example notebooks based on what you're trying to do. So you can just search for single cell, VCF, understand our APIs, etc.
I think that's the list of our questions. Wonderful. Thank you again, Jeremy, Chase. It is now time for our raffle, and we have a winner, Sekar Duraisamy. So you get a $100 gift card from us. You'll hear from us. Congratulations.
Ah.
Actually, I do have one more question that I see here. So we do have time, so let's take that. It is clear that TileDB has a lot of advantages, but what if we want to talk about N+1? How is TileDB different from iterative genotyper of Dragon Illumina?
Right. So there's that N+1 problem in databases is one thing. So that's essentially you add a new column, and then for every row, you have to visit that row and then expand the size of the grid to that row. In bioinformatics, the N+1 problem generally points to something where you're introducing a new sample, and that sample might introduce variance into the mix where we have to evaluate every other sample to see if they either are referenced for that position or unknown. So we have no read coverage at that locus. Okay. So TileDB has first-class support for GVCFs. So if you have VCFs that have these reference ranges that kind of distinguish, calls from reference calls, we'll accept that natively and faithfully, and actually allow you to do queries that reveal allele count frequencies or other things reliably, even if variants fall into those reference ranges. So we don't necessarily support joint genotyping in TileDB VCF, but if you did have a multi a multi VCF, so something with a multi-sample VCF that has been joint genotyped. So for quality or for controlling for batch effects or other upstream problems, we'll accept that. We actually have routines that'll split that and ingest samples individually. So I hope that kind of answers your question.
Yeah, and I think that ingestion stories too is something that I see is really a huge value, right? Especially when you can programmatically point to something to ingest and let us scale it up and bring it into the file format. And then once you scale up that compute, it's serverless, it frees up resources, and then it's cataloged right within your system. And I think that's definitely something that a lot of customers I work with really enjoy about the platform and really like.
Wonderful. Thank you again. Thanks everybody for joining us today. We will see you soon on another one of these tech talks.
Sure thing.
Thanks, everyone.